Every morning you open a shared inbox that filled up overnight, and you have to sort each message into the right pile. Some of it is urgent. Most of it is not. You have done this so many times that you barely read the whole message anymore. You skim 2 or 3 words and you already know where it goes, and the ones you get wrong cost somebody half a day of waiting. So how do you actually know? You do not have a rule that covers this message. You have a memory of thousands of messages that looked a little like it, and what turned out to be true about them. Hold that question about how the skim works, because we will come back to it in the last 2 minutes. Something strange is waiting there. The method underneath that skim rests on a claim about your data that is flatly, provably false, and it is still quietly sorting a great deal of text in production this week. Why would a model that is wrong about the world beat models that are right about it? You already know the shape of the bad version, since you have probably shipped it. Somebody asks for automatic routing, so you write rules. If the subject line carries the word refund, it goes to billing. If it carries the word broken, it goes to support. 2 weeks later there are 40 rules, they contradict each other, and nobody wants to touch the file. Who owns that file when Rule 31 and Rule 39 disagree, and how many hours will they lose to it? So let us give the thing a name and keep it for the whole episode. Sortwell is the small service a 2-person team runs to answer exactly one question: which queue does this message belong in? No rules file. No thresholds tuned by hand. Sortwell has read the last 20,000 messages your team already sorted correctly, and it has counted words. That is all it does. It counts. Ask why counting works and the easy answer arrives immediately. Sortwell works because spam looks like spam. Simple. And it does sound like it says something. But we should really avoid explaining a method with the same word we are trying to explain. Looks like, in what sense? 2 messages do not resemble each other. They are characters in a row. Before anything can look like anything, you have to say what you are comparing. Let's try again. Take 2. Sortwell asks a narrower question, and it is one you can answer with nothing but counting. Given that a message landed in the billing queue, how often did the word refund appear inside it? That is a number you can look up in your own archive this afternoon. Now flip it around. Given that the word refund appeared, how likely is billing? That flip is the entire trick, and the 2 numbers are not the same number. That flip has a name older than every technology in this sentence. Thomas Bayes wrote it down as a rule for updating a belief when new evidence arrives, and Pierre-Simon Laplace turned it into the working form everybody still uses. Put plainly, the chance of the queue given the word is proportional to the chance of the word given the queue, multiplied by how common that queue was to begin with. 2 pieces, and each is just counting. How common was each queue before you looked at the message at all? That is the prior. How surprising is each word inside each queue? That is the likelihood. In other words, one describes the world you started in, and the other describes what this message adds to it. Multiply the prior for a queue by the likelihood of every word in the message and you get a score for that queue. Sortwell computes 1 score per queue and keeps the biggest. That is the entire algorithm, and you could build it in 1 afternoon with a dictionary and a loop. Let's put numbers on it, since the arithmetic is where the intuition lands. Suppose your 20,000 sorted messages split 3 ways: 12,000 support, 6,000 billing, 2,000 legal. So before reading a word, support is 60% likely, billing 30%, legal 10%. Now a message arrives carrying the word invoice. Counting says invoice showed up in 900 of the 6,000 billing messages, and in 120 of the 12,000 support ones. So for billing you multiply 30% by 15% and get 4.5%. For support you multiply 60% by 1% and get 0.6%. Billing wins by roughly 7 to 1, and notice what did the work. Not the prior, which favored support 2 to 1, but one word 15 times more concentrated in one queue than the other. Analogy: think of it as a jury that never confers. Each word is a juror who has seen many past cases and votes for one queue with some confidence. Nobody ever checks whether 2 jurors are repeating the same observation. The votes are simply multiplied together, and the loudest total wins. And there is the lie, sitting in plain sight. Multiplying those probabilities together is only valid if the words are independent given the queue, which means knowing a message contains the word invoice tells you nothing about whether it also contains the word payment. Is that true of any language you have ever read? Of course not. Invoice and payment travel together. Purchase and order travel together. Every real sentence is a web of correlations, and this model flatly denies the web is there. So why would anybody ship a model built on a claim they know is false? That denial is what the word naive is doing in the name. It is no insult and it is no hedge. It is a precise statement of the one thing being pretended. Naive Bayes is the Bayes rule plus the pretense that your features never talk to each other. Note that pretense has a measurable cost, and it is not the cost most people expect. It does not cost you the answer. It costs you the confidence attached to the answer. When the same evidence gets counted 3 times because 3 correlated words point the same way, the winning score inflates past anything defensible. So Sortwell will tell you a message is 99% billing when a defensible number is closer to 80%. Which of those 2 numbers has been sitting in your dashboard? But look at what a classifier is actually asked to do. Is it asked for a trustworthy probability, or only for a winner? It is asked which Q, and that is a question about ordering, not about magnitude. You can be badly wrong about how much you believe each option and still be entirely right about which one you believe most. Inflate every score by a different wrong factor, and the largest one very often stays the largest. That is the whole resolution of the puzzle, and it is worth saying slowly. The independence pretense wrecks the probabilities and frequently leaves the ranking intact. A model can be a terrible instrument and a fine decision rule at once. So which of the 2 do you have right now, and what in your training loop would ever tell you? Case in point, Domingos and Pisani in 1997 showed this classifier winning on datasets where its own independence claim was violated everywhere, and explained why. The 0-1 loss you were scored on only cares which score came out on top. But ask a different question of the same model and it falls apart. Ask it to rank which of 2 messages is more confidently billing and you are back to trusting numbers you should not trust. So why did this particular method get famous? The reason is a constraint rather than a theory. In the late 1990s, junk mail was winning, and the filters were handwritten rules that spammers could read and walk around. A Microsoft research paper by Sahami and colleagues in 1998 suggested counting instead of legislating. In 2002, Paul Graham wrote a widely read essay called A Plan for Spam that put the idea in front of every working programmer at once. Look at what that problem demanded, since that is what selected the method. Every user needed a personal filter, as one person's newsletter is another person's junk. The filter had to update the moment somebody clicked the junk button. It had to run on a mail server handling thousands of accounts. And could a support agent say out loud why a message was held back? Counting satisfies all 4 almost by accident. Training is one pass over the data, so a filter per person costs nothing. Adding a new example is a handful of increments, so learning from a single click is immediate. Scoring is a lookup and a sum. And you can print the 10 words that push the decision, which Hill Forest of decision trees could match at the time. So the honest history is not that somebody proved the pretense was safe. Nobody did. The method spread because it fit the shape of the deployment, and the accuracy was good enough that the theoretical problem never got in the way. That is how a surprising number of durable tools arrive. Now, counting has a failure mode that will bite you inside the first hour. What happens when a word in a new message never once appeared in one of your queues? Its likelihood for that queue is 0. Multiply anything by 0 and the whole queue is eliminated, on the evidence of one word nobody has seen. One novel token, and the whole category is dead. The fix is a single line of code and it carries Laplace's name. Add 1 to every count before you divide, so nothing is ever exactly 0 and nothing ever exactly certain. It gets called add-1 smoothing, or additive smoothing when you use a fraction. It looks like a hack. It is closer to a confession. Your 20,000 messages are a sample, and a word you have not seen is unlikely rather than impossible. Caveat: how much you add matters far more than people admit, and the right amount depends on how large your vocabulary is next to how much text you have. Add a full 1 to every count across 60,000 features in 200 rows, and the smoothing drowns the signal you were measuring. Hold on to that, because it is the same problem in a different coat, and it comes back before the end. There is a second practical trap and it is quieter. Multiply 500 small probabilities together in floating point and the result underflows to 0, which means your classifier silently returns the same answer for every input. So nobody multiplies. Everybody adds logarithms instead, which turns the product into a sum and the whole thing into a linear score. Notice what that makes it. A linear classifier, in the same family as logistic regression, arrived at from a completely different argument. In practice, there are three variants you will meet, and choosing wrongly costs real accuracy. Multinomial counts how many times each word appears and is the default for text. Bernoulli only asks whether each word is present or absent, and it beats multinomial on very short documents like subject lines. Gaussian assumes each numeric feature follows a bell curve inside each class, which is what you reach for when your columns are measurements rather than counts. Quick win: before reaching for anything heavier on a text problem, spend 20 minutes fitting a multinomial model with add 1 smoothing and keep it as your floor. Scikit-learn ships it as multinomial NB and it trains on 100,000 documents in a few hundred milliseconds on a laptop. If your gradient-boosted ensemble cannot beat that floor by a margin you would defend in a review, you have learned something more useful than a leaderboard number. Here is one more place it quietly wins, and not the place you would guess. When you have very little labeled data, a model that makes a strong wrong assumption often beats a flexible model that makes none. The flexible one has enough freedom to fit the accidents in your 200 rows. Sortwell has almost none, it can only move a handful of counts around, so there is very little to overfit. The pretense acts like a brace. It is wrong, and it is also holding the thing up. That trade runs the other way as your data grows. Give a flexible model 100,000 labeled examples and its freedom becomes the entire point, since now it can learn the interaction Sortwell is forbidden from seeing. So which model to reach for is a question about how much labeled data you have, not about which method is better in the abstract. And if you do keep this model, the interactions have to come from you. If pairs matter, put the pairs in as features, so payment overdue becomes one token with its own count. Drop words that appear in every queue, since a juror who votes the same way in every case adds only noise. Every improvement here looks like plumbing rather than modeling, which is exactly why it gets skipped. So where does the naive pretense stop being harmless? Watch what happens when you duplicate a feature. Copy one column, feed it in twice, and the model counts that evidence twice, since it was told that two columns are unrelated. A human reviewer would notice. Sortwell cannot. Redundant features, accidental or deliberate, are the cleanest way to make this model confidently wrong. It also breaks when a decision turns on a combination rather than any single piece. If a message is urgent only when it mentions both a service outage and a customer name, and neither word alone means much, then a model that refuses to look at pairs cannot represent the rule you care about. That is not a tuning problem. It sits outside what the model is able to say. And it breaks on anything that needs the probability itself rather than the winner. If you want to hold back the cases the model is unsure about so a person can read them, you need the number to mean something, and here it does not. Fit a calibration step on held out data before you build a threshold on these scores, or you will be filtering on noise and reporting it as confidence. There is a quieter failure that costs teams months. Your priors come from whatever mix of messages you happen to have when you trained. When that mix shifts, and it always shifts, every score shifts underneath it. A queue that used to be 10% of traffic and is now 40% will be underpredicted until somebody refits, and no alarm will fire. Which brings us back to the question from the opening. Why does your skim work? Because you were never doing what you thought you were doing. You were not weighing the whole message. You were taking 2 or 3 strong signals, treating each one as though it stood alone, and picking whichever conclusion got the loudest total. Your skim is Sortwell. It always was. And the reason your skim is usually right is the reason the model is usually right. You are not producing a number anybody will audit. You are producing a decision, and a decision only needs the ordering to survive. So the real question is not whether the assumption is true, since it never is. Ask yourself instead what you are going to do with the output. If you need a ranking, a wrong model with the right winner is a fine tool and a remarkably cheap one. If you need a number somebody will act on at a threshold, this model may still mislead you badly, and no amount of extra data will fix it, because the flaw sits in the pretense and not in the sample size. That is your call to make, and it is worth making out loud, in front of the person who will be paged when it is wrong.